Okay, we're working. What's up? Yes, you can open your eyes now. Oh yes, sorry. Okay, everyone who closed their eyes, you can open your eyes now. Thank you. You're ready to look at the very obligatory product safe harbor statement. So everything that you see could be a lie. And so please don't tweet this, and any forward-looking statements are subject to change. But no, actually, Joe and I are both here, so let me actually go to the next slide. We're going to talk about deep dive into Delta Lake and UniForm. Hopefully you all are in the right room. I know that we have 90 minutes ahead of us. I'm very excited. We have some totally well-planned surprises in store. First, introducing myself, I'm Michelle. I'm a product manager here at Databricks, based in San Francisco. I work on Delta Lake. You can talk to me about Delta Lake stuff. You can also talk to me about Unity Catalog interoperability stuff. Have a couple other breakout sessions on that on Thursday. And then you can also talk to me about the best burritos in the Mission neighborhood. If you're not a San Francisco local, I can point you to the best spots.
All right. And my name is Joe Wyden. I'm a Principal Solutions Architect. I've been at Databricks since 2017. Before that, I had a little pit stop at Hortonworks, and before that, I worked at Capital One. I am the proud owner of the smallest contribution to Delta Lake. It is a single line, and you can find it in Delta Lake 1.0.0. I focus at Databricks helping our clients use Delta Lake and really push the limits, and oftentimes that dovetails into the second part, where I like to help our clients use the latest features like deletion vectors and the change data feed and all the fun stuff we're going to talk about today.
This is the fun stuff. Okay. Let's see if the clicker works. Uh-oh, I'm not getting it to work.
We don't have a
All right, I guess we just have to do it on the manually. Okay. So there's 5 things that we're going to talk about today. Intro to Delta Lake and core capabilities. Hopefully what you all are here for. Unpacking the transaction log protocol. We're going to deep dive into that. Some of the recent innovations on top of those core capabilities. And then we're going to talk a little bit about some real-world customer use cases. And then finally, share a sneak peek of the upcoming, very exciting roadmap that we have for Delta Lake. And so we're also going to try to pepper in some fun interactive pieces. So first, I want to ask everyone, we're going to do this as a test. Do you prefer cats or dogs? Everyone, please whip out your phones. Go to this QR code, and then we're gonna try this. We're gonna try this out. So everyone's scanning it. Hopefully I think you have to join. Oh shoot, do I have to give you some code, or are you able to just join? I might have to give you a code, so just, is everyone in? It works? Okay, great. So then now, let's see if it works for me to go, oh God. How do I? Okay. All right. Oh, everyone's voting. Okay, great. Oh, this is wonderful. This is actually working. 75% dogs. Are people? Yeah, people are not really cat people.
I think a lot of people would have chose both if they could.
Oh, really?
Yeah, we got a bunch of bothers.
Okay. Well, more people. I think people are feeling bad for cats now. I see more cats. If you voted for cats, why? Shout out why. They're cute. Okay. Well, dogs are cute too. I thought I showed an adorable photo of both a kitten and a dog. Okay. Next question. What's your familiarity with Delta Lake? We have, the first option is what is Delta Lake? The second option is I know some things. Third is I know enough to ask hard questions, but we're not doing a Q&A today. And then the fourth is expert level, ask me anything. Who's the expert? Who wrote expert? Why are you here? Okay, I know some things, so that's good. And then we got some what is Delta Lake, so that's good. I'm about to cover that right now. And then I know enough to ask hard questions. We're gonna have enough for you too, hopefully to make those questions even harder. So I'm gonna switch back. That was a good tech check. I have no idea how to do this. I just hit slideshow. Oh my god! All right, we're gonna nail it. The 4th or 5th pop quiz that we have. Oh, I guess I have to control.
You gotta do the slides.
Okay, yeah, I can do the slides. Okay. Go back over here. Okay, so for those of you who said, what is Delta Lake? I have the answer for you right here. Delta Lake, especially with UniForm, we're gonna talk about UniForm too. It's an open storage format that brings performance, interoperability, and ACID transactions to open data lakes. So a quick history lesson here. Back in 2017 is when we started developing Delta Lake, and then we fully open sourced it back in 2019, or was it 2019, yeah, fully open sourced it back in 2019. And so what that means is that you get all of these key features: ACID transactions, scalable metadata handling, unified streaming, batch data processing, on top of a fully open storage format that you can store in a storage service that you own and control, such as S3 or ADLS. So some sort of blob storage that you control. It's basically, well, underneath the hood, it's all just files that you have, that you can see, that you can go find yourself. And then you can go use it with whatever engine or tool or platform that you want. It's all open. And so since 2021, I don't know why I put 2021 here, even though I just said 2019. But since 2021, we have continued to innovate and grow the community. And so we recently hit a very exciting milestone, which is that Delta Lake now has 20 million downloads per month. Yes, take a picture of this slide. This is a good slide. I didn't put it together. I actually stole it from someone else. But this is really exciting. I mean, basically, this is a very thriving community, and we're continuing to see tons of innovation and folks building on top of Delta Lake. And so come some quick stats on our community: 11 repos in the project, more than 50 releases, Delta 4.0 coming up, and then also a very active community: 9,000 GitHub stars, 500 contributors. And then here's actually the best one. We worked really hard for this, is 50,000 members on LinkedIn. It took us a really long time to get there. It's really hard. We're trying to grow our thought leadership on LinkedIn, so please also make sure to follow Delta Lake on LinkedIn and join the community, especially if this talk intrigued you and you want to learn more. And so this is going to be a quick preview. I mean, we're going to dive into a lot of these, but Delta Lake innovation continues. Things like deletion vectors, Delta UniForm, we're going to talk about all of those, and then some of these upcoming items on Delta 4.0. Yeah, this is also a money slide. Yeah, you're going to see it in a lot of other breakout sessions too, probably. Cool. Okay, we're going to talk about all of these. And then, finally, this is super important. Interoperability between formats is very important to us. We're going to spend a lot more time talking about this because you might have heard, okay, there's Delta Lake, that's one storage format. There's also Hoodie. Not Hootie, by the way, it's Hoodie. I'm pretty sure because they have some stuff that's like hoodies, the hoodies you wear. And then also Iceberg. And so, we think that it's really important that there's interoperability and compatibility between these formats. And so we're going to talk a little bit more about Delta UniForm too, upcoming in this talk. Okay, another pop quiz. I think this is a check on whether or not you were paying attention to what I just said, is what I think this is. So let's try it out. Okay, go back to the thing, and then yes. How many contributors to Delta open source? I actually think I may not have said this out loud. Oh my! Everyone knows? No, sorry, I shouldn't have said that.
Jeez.
Oh no. I just gave it away. Yes, over 500 contributors to the open source Delta project. I really should have not have exclaimed right there. Okay, and then I think with that, I'm gonna go back to, no, wrong one. I'm gonna go back to starting the slideshow, and then, wait, shoot.
Practice makes perfect.
Yeah, we're going to do a repeat of this talk, and so it's going to be really good for the second one.
Thanks for getting the guinea pigs. All right, and now we'll get to the densest subject. So in most talks, I feel like they put all the dense stuff at the very end. I think that's a terrible idea. I like to talk about the dense stuff at the beginning because you just had some coffee. At the end of the day, you're ready to go home. Right now, you're super excited to learn about Delta Lake. So we're going to talk about the transaction log. So Michelle mentioned a bunch of key features that Delta provides. So things like ACID transactions, things like scalable metadata, things like schema enforcement, things like unifying batch and streaming. All of this is really possible because of the transaction log. So the transaction log is really the core to a lot of the functionality. When we take a look at what Delta Lake looks like on disk, you actually see some things that are familiar, maybe, and some things that are a little different. So if we take a look, if you guys go ahead and do a listing on a Delta table, you'll see many or all of these things in your Delta table. And Delta takes all this information, combines it all together to basically give you those features. So there's a lot going on here, but if we kind of chunk it up into bits, if we take a look at it and break it down, the first thing we have in the table directory is the Delta log. So we're going to talk a whole bunch about this and get really deep into it, but this is where we store all the information about what files have been added to a table. Within here, we have these things called commits. So every single time you write to a Delta Lake table, it tracks what's been written to the table, what's been removed to the table. And it's done this in the form of a commit, which is a JSON file. As many of you may have noticed, when you're working with really, really large tables on S3 or ADLS or GCS, when you do large listing operations, they can get really expensive and take a long time. So we do some little tricks, like putting little pointers to latest files, so that when we're interacting with this and you're trying to do sub-second queries or sub-5-second queries, they're actually possible. Now with Delta Lake, that was kind of like the core bits. We've since added on a lot of different features on top of it, and those different features manifest data in different locations. So the first one, which we're going to talk about, it's a super cool feature, is the change data feed. So if you guys are familiar with a data warehouse or a database where you have like a bin log, Delta essentially has a bin log. So instead of reading the entire table and trying to grep changes through joins, you can actually just use the bin log or the change data feed to get that. Delta Lake does support partition directories. So some of the older optimization techniques like partition pruning still apply to Delta Lake. You do have the actual data, so we're going to talk a bunch about UniForm, and a Delta table is just really a transaction log, a couple extra bits of data, and then the data itself, which is stored in Parquet. And then finally, one of the coolest features, we have deletion vectors. So when you're working with these large data sets and you do mutations, maybe like a CCA or a GDPR request, and you need to delete records about a user or a particular entity, instead of rewriting the entire table, you can actually pack these deletes into little deletion vectors so that when you do several of these in a row, you're not rewriting the table every single time. So it's a super powerful feature. All right, so we have all of that. A Delta Lake table is a combination of all of those different bits. They get aggregated together, and the Delta metadata generates the current metadata, a list of files, a list of transactions, and a version. So when you query a table, it has a stable version. So if you have multiple readers and writers, you have some level of consistency with the ACID guarantees that you get, and we do that with the version. All right, so I mentioned, we're gonna go deep into the metadata, but I mentioned that the metadata is really what makes Delta Lake be able to do what it can do. So I mentioned there's these things called commits. Commit's just a JSON file that contains information that has actions. So an action is just something you do to your Delta table, be it you add data, you remove data, you upgrade the protocol. There's a couple others that I'm blanking on. I think there's 6 actions in total. Oh, you change your schema. So those are all called actions, and they manifest in the commit file something like this. So you can see in this example, we did an insert into a table probably. We went ahead and added data. So the add right there is the action that we did to the table. In that add file, we actually store additional metadata. So in this case, we store the path to the file. We have the ability to store partition values, the size of the file, when it was modified. A really interesting one, if you've ever kind of dug into it, data change. So if you ever work with your data and you change how it looks, but you didn't actually change the data, so maybe you optimized it, you sorted it, but you didn't actually change or remove data, you can just mark data change false, and it behaves a little differently. It's really cool for like when you do streaming, you do backfills, that's like key. We have a base row ID, we have a commit version, And then one of the coolest things when we talk about performance of Delta Lake is going to be stats. So we'll get deep into it, but the stats are basically what gives you to do the really low-level file skipping. All right, so we mentioned Delta had ACID transactions. So what does that mean? Basically, there's a set of prerequisites that you need to adhere to say you have ACID transactions. So the first thing in Delta is how do we implement atomicity? So we do it through commits. Every time a writer commits to the table, it's going to go ahead and write a new commit file. We'll go ahead and increment, so you can see this case, 000 would be the first commit to a table, 001 would be the next one. Serializability is actually super important. So when you have multiple writers that are writing to the same table, you all need to agree what order data was written. So Delta Lake will go ahead and basically implement this for you. So in this example, we have a user, 1, who is going to read the version 000 of the table. They're going to try and mutate it. So maybe they do a merge, they do an update. But while that's happening, user 0 comes in and says, hey, I'm also going to do something. And whatever they did was a lot smaller. Maybe they used deletion vectors and the other person didn't. And they were able to commit the next change first. So Delta Lake is able to say, okay, user 1, you read this version. You're trying to commit against that version. User 2 has already updated it, so I need to fail user 1. And that's actually how we do all of our conflict resolution. So with Databricks, with Delta Lake, it's optimistic concurrency control. So we don't put a lock on a table, although some of our customers have figured out ways to put locks on a table. But out of the box, we don't put locks on the table, and it's all loosely based on who commits first. So in this example, kind of just reiterating what I said, every time you read from a Delta table and then you write to the Delta table, we go ahead and we record the start version. When you go ahead and attempt to commit to the table, we take a look and see, did the table change? If the answer is no, it's not the end of the world. We then go ahead and we say, did anything that you read change? And if the answer is yes, you'll get a concurrent update or modification example or exception. And then you can try again. If the answer is no, nothing you read, Delta Lake will just go ahead and commit it, and it'll just increment it. All right, pop quiz.
All right. Let's see. Okay, the true or false question.
Delta Lake uses pessimistic concurrency control. All right, we haven't lost anyone yet. Well, we've lost a couple people, it looks like, but.
Okay, what's the answer?
Delta Lake uses optimistic concurrency control, so this is false.
All right, we caught 14
That's like a 90%.
people sleeping.
That's an A, right?
Oh, okay, yeah.
That's an A.
Yeah, I guess you didn't grow up in an Asian household. I'm sorry. Sorry, this is recorded. Never mind.
Michelle Leon, everybody. Oh, what do we do? All right, so that metadata. We were talking about adding files. We're talking about changing schema. Some of the metadata is pretty small. Some of the metadata can actually get quite big. So if you think of a table where you have, say, 1 million files, we have 1 million of those add file actions that happened, and that's stored in the commit log. And a good rule of thumb is the max size of an add file is 5 KBs. Usually it's never bigger than that. So when you're working with millions of files, and each time you add it, it generates 5 kilobytes of metadata, that actually in itself becomes kind of big data. 5 KB times 1 million is 500? 5 megabytes? No, what is it? 5 gigabytes, okay. Yeah, so that's actually pretty big in itself. So the way Delta Lake goes ahead and handles that is we figured, why don't we just use a distributed computing system? And at Databricks, we happen to have one called Spark. So actually, a lot of the metadata processing that happens and why it's so scalable is because we use Spark to process the metadata, and then we use Spark to process the data. So this can actually scale pretty big. And I want to say the largest Delta table I've seen had almost 100 million files. So they can get pretty big. All right, so I told you it gets dense. When we're working with a table, at the very beginning I said a table is a collection of actions, which is just the metadata kind of aggregated together. So if we were to think about what happens when the processing actually happens, you have a user that's going to come in and query. The latest version of the table is version 7. Well, what we need to do is we need to go ahead and read 0, 1, 2, 3, 4, 5, 6, and 7, and combine them all together. So what you'll see is that we actually read all of them, and then we generate the table state, or the state of the table at version 7. And this, again, has all the information about the files, the statistics, the partition columns, the schema. So we have that kind of cached version. And then we'll go ahead and add more data. So we have a cluster that's up and running. It has that version 7 table state that's cached. You then have another user come in and they do a bunch of updates to the table, or they do a bunch of appends. And all of a sudden, we get to what's called a checkpoint. So a checkpoint is a way to take all of that JSON data. JSON's very verbose, kind of bloated if you ask some people. And you take that data and you put it into a Parquet file. And it allows you to really kind of compress the amount of data, really reduce the size of the data. So these checkpoints actually add the ability to scale even further. So when we did do that update with the checkpoint, we'll go ahead and read the latest checkpoint. And instead of replaying everything, we just take the checkpoint in the next 2 files. And in this case, we'll go ahead and generate that table state and cache the data. So I kind of alluded to this, but what happens when you contain many thousands of commits? So periodically, we're going to go ahead and checkpoint it. And as we do the checkpointing process, we put a little pointer into the Delta log, which is the last checkpoint file. That last checkpoint file tells the reader what's the last known checkpoint file. So when we go ahead and we do all that listing, instead of listing from file 00000.json to 10,000 or 201 in this case, we can actually go what's the latest known checkpoint and list from there. So all of these little tricks are being played to basically make all of this metadata super scalable, but also support some of your low latency queries that you're going to go ahead and do. So with this commit log comes a really cool feature, time travel. For time travel, it's basically saying, I have this table, maybe table version 201. I want to go ahead and look at it as if it were table version 199, or I want to make it, I want to go ahead and look at it as of yesterday. So with time travel, we can use both a timestamp and a version number to go back in time and look at the table as if it didn't even have those last 2 or last 3 commits, however far you want to go back. And for this particular one, so you'll see it's available in SQL and data frame. Select star from my table, version as of 500. And I think if you guys remember from Michelle's pop quiz, Delta Lake has more than 500 contributors, so that's why we have 500 in there. And we also have the ability to time travel by timestamp. This is kind of far more popular. It's way less common to know like what version are we on. And it's like I really just want to know what it was like yesterday. With the exception of machine learning, those people usually pin the version, so they have that. But with timestamp, it's the same thing. We go ahead and you can run select star. And the way timestamps work are just slightly different. So with the version number, it's very easy to go to the Delta log and say, okay, go ahead and give me the snapshot of the Delta table at version 500, because it's commit 500, right? Super easy. Well, we don't necessarily store the timestamp as a file path. So when we're working with timestamps, we can't just say, go ahead and get snapshot 509. We actually need to figure out what timestamp or what version is at our timestamp. So as we are committing these tables, or these commits to the table, we actually do track some of the timestamp in the metadata. So in this case, you'll see 2019, 10/16. Who wants to guess what happened that day? That was the day we donated something. We donated Apache, I'm all over the place. We donated Delta Lake to the Linux Foundation. Then we have JSON 1071, and that's May 24th, 2021. Who wants to guess what that was? All right. Delta Lake 1.0 is officially released. All right, then we have July 20th, 2022. Who wants to guess this one? What comes after 1? 2. All right. And then we have a date that's actually behind it. What do we think happened at June 30th? Nothing, I just needed a date to go back in time. So, but what's interesting here is we have our ordered commits, and I said we all have to agree what order everything goes. And we also have these timestamps, and these come from the storage system modification. And this timestamp is after the timestamp before it. So how do we make sense of that with time travel? So what we do is when we have out of order timestamps, we go ahead and we just add 1 millisecond to the previous commit, so you have that kind of congruity. Now, when you're working with timestamps, we have what we call the Price is Right rules. So when you go ahead and you ask to query a table by timestamp, we get the closest timestamp that doesn't go over the timestamp. So it's always just before the one you mentioned, or exactly if you happen to know the exact timestamp, then you should know the version, so use the version. Yeah. All right. Pop quiz.
Oh, another pop quiz.
You know what you mean.
All right, I can do it. Okay, y'all. Which of the following do not belong in the delta log? Add files, partition columns, query optimizer slots, file statistics. I think let's keep waiting for getting. There should be more than this many people in the room. You're all waiting to see what everyone else votes, huh? Oh, you don't have the QR code? Oh, no. Oh, we're taking down the Wi-Fi. Okay. Okay, then we'll wait. Okay. That's good distribution. Okay. Oh, they're still coming in. What do all these thumbs up in the bottom right-hand corner mean? I don't know. But anyways, what's the answer, Joe?
Oh, the answer is the query optimizer stats.
Oh, all right. So
this
most
looks-
people got it.
This looks like a C. What's that in the Asian household? All right. All right, so transactions and really the reliability that they give you is great. One of the things I didn't even mention about transactions is transactions only happen after you've written all of the data. So if you go ahead and you write to a delta table and it fails halfway through, well, the transaction never gets written. So when a reader comes in, they don't even know that that data exists. So there's lots of like neat little reliability things that are also in Delta, but there's also a lot of performance things. And the best way to kind of talk about that is let's take a look at what information you need when you plan a query. So if you're using, this is gonna be a Delta Lake versus a Parquet source. And we'll also look at where you get this information. So when you're working with these different table formats, the first thing you need is schema. And when you're working with Parquet, if you've registered it with Hive, you can go ahead and ask Hive, what's the schema of this table? And that's okay, but if your schema changes, you either don't get that extra row, or excuse me, extra column, or you have to go ahead and update Hive Metastore. Or if you don't have Hive Metastore and you just kind of YOLO read and pick up all the Parquet files, well then you have to do an inference from all the Parquet footers. With Delta Lake, it's stored in the transaction log. For partition columns and the values of the partition columns, if you're used to using Hive Metastore, you probably run an MSCK repair pretty often, or you implement your own ACID with an alter table add partition. That works, but it's rough. I remember when I was first learning Hadoop and I wrote to a partitioned Hive table and nothing was in there after the write. That was, learned something that day. The nice thing about Delta Lake is it's just stored in the transaction log. So if you go ahead and write to a partition, you don't need to tell the Metastore that there's a new partition. It's just stored in the transaction log. All right, this is a really big one coming up here. So the files to read. What files do you actually read when you query a table? When you're working with a Parquet source, you have to list all of the files. That's fine if you have one file. It's okay if you have 10 files. 100 files, not a big deal. 1,000 files, okay, I've been waiting a few seconds. 10,000 files, start counting in minutes. 100,000 files, we're just not gonna run this query. This one's actually, I feel like, underappreciated. Listing files is such like an expensive operation that if you don't have to do it, you should never do it. So in Delta Lake, we just store the path to all the files. And when you need to go ahead and retrieve a file, we already know the path name, so we just get it. We skip the whole listing entirely. When you do the Parquet source, you gotta list it all. And in Delta Lake, it's stored in the transaction log. All right, then we have file statistics. So these are min and max values about the file. With Parquet sources, you can argue they exist, but you have to go read this thing called the footer and then get the statistics, but you still have to read something, you have to list something, you have to get something. With Delta Lake, it's all stored in the transaction log. And then the last one, maybe this is a win for Parquet, so protocol. So Delta Lake is really a protocol that just says, you need to do these things to generate a table. When you write to a table, you need to do these things. When you read from a table, you do these things. When you checkpoint a table, you do these things. So we store that in the transaction log. For Parquet, you don't have to do that, but win some, you lose some. All right, so we talked that there are a bunch of different actions that you can do. Let's go ahead and talk about those 5 different things we mentioned and what they look like in metadata. So the first thing we want to do is we want to go ahead and get the schema of a table. So every time we make a change to the schema of a table, so when we create the table, we define a schema. When we go ahead and we add new data that has a new column, we do an update on our metadata, a metadata action where we change the schema string. When we go ahead and we read a table, we just go ahead and collect all of these schema strings. And I mean, there's obviously a few other things in here. We go ahead and generate the schema from that. So that's how we get the schema from the transaction log. And actually a really cool feature is if you use time travel and you go back before this commit happened, you will have the old schema of the table. So if you overwrite a table and you have this new table with, you put merge schema, and I think there's like ignore schema or update schema or something, and you completely mess it up, you can actually go back in time, go to the old table, look at the old schema. So it's actually pretty cool. The partition columns. Oh, I didn't even mention how you do this in Parquet. So when you're working with Hive Metastore, you either do the MSCK repair thing, or you do a bunch of directory traversing to generate the partition values if you're reading it from the path. With Delta Lake, it's just stored as an option. It can be null. You don't have to use partitions. And we just store that directly in the transaction log. The list of files to read. When we do this, it's stored in the transaction log. We have a path of all of the files. And Delta Lake then takes that list of paths, or the list of paths, we pass it to Spark, and we go ahead and process them, skipping that lengthy listing issue. One of the really cool things, and we'll talk a little bit about it deeper, when we collect these file stats and these paths back to the driver, when we go ahead and we plan our query, we actually run our first level of data skipping. So we prune out all of the files that aren't the right partition value. We prune out all of the files that have min and max values that don't fit the predicate that we're looking at. You can eliminate a ton of data before you even get to the data, just using this metadata. All right, and what about small files? So the small file problems still exist. You'll actually see we have the size of this particular commit, 841 KBs, and it's only one record. So, small files happen. They happen quite a bunch, and they're relatively not fun to deal with. So Delta Lake actually realizes there's got to be a better way to do this. So with Delta Lake, we have a utility command called optimize. And what optimize does is it optimizes all those small files from a bunch of little files into fewer big files. And what you'll notice here is in the metadata, we go ahead and we remove those small files, and then we add the newer big files in the metadata. So if a user is reading this data before the optimize happens, they'll look at the small files. If the optimize finishes and another query starts, they'll start looking at the big files, or the bigger files. So it maintains all of that ACID. The transaction guarantees you don't disrupt people while you're even running these optimization queries. So if you've worked with some big data technologies in the past and you had a user that's querying a table and you're running your own compaction and you do take a partition, you go ahead and you rewrite it in the alter table, put it back in, and the user gets a file not found exception because you went ahead and updated the data and there's no transactions in that system. With Delta Lake, you can do all these maintenance operations while people are interacting and using the data safely. All right, so performance. So data skipping is a big thing when it comes to performance of large tables. So how do we get rid of as much data as possible, process the least amount of data, and go ahead and get the correct answer? So one of the very well-known techniques, every big data tool uses it or should use it, is partition pruning. And for the folks that aren't super familiar, partition pruning leverages information from the directory structure to go ahead and basically say all of the data for this particular value exists right here. So in this example, we have a partition table on the column named part. Hindsight, not a great name. It'll have part equals 1 in the directory structure. That means everything in the red highlighted files has the value part equals 1. And then you'll see part 2. So when we go ahead and query, we can go ahead and say, when I select star from this table where part equals 2, go ahead and skip every file where part equals 1 and just give me the files that part equals 2. So that's okay, but Delta Lake takes it to another level. Delta Lake uses a pretty simple but well-known I/O pruning technique. So I mentioned we track stats as we're writing our tables or all of the files to our table. We collect min and max and number of values, and we store that information. And if you were to kind of transpose it into a little chart, it would look something like this. You'd have a column with an equally bad name call, and in that we would have a min and a max value for call for every file. So when you go ahead and run a query, and in this case, let's do where column equals 5, it'll go ahead and say, okay, the minimum value in here is 6, so I can skip that file. The max value in 3 is 4, so I can skip that file, and I only need to read that second file. So that's great, but then, we have this data coming in, and it doesn't come in how our users want to query it. It just kind of comes in, and it comes in how it comes in. So there is something that Delta offers called Z-ordering. So Z-ordering is a way to basically sort the data so that in addition to partition pruning, you can make file skipping and data pruning super, super effective. So we'll talk a little bit more about Z-ordering and liquid clustering a little bit later. But this is super powerful. Now if you ingest your data by date and your users want to query by user ID, instead of trying to partition by user ID and having really small files, you can Z-order by user ID. It'll put ranges of values for every user ID in files, and then when you go for user ID equals 1, the stats will actually filter out 99% of the data. You don't have to do anything, it just kind of happens. And here's an example. But Z-order isn't perfect. When we do a Z-order, you can Z-order by multiple fields. The more fields you start to Z-order by, we store ranges of values, and for the first dimension. The second dimension, we store more ranges of values. And Z-order works by kind of drawing a line through everything, like a 2D space. And then we flatten out that line, and we store a section of that line as a file. So that works okay. But with Z-order, sometimes the ranges can get too big. You might have chosen a bad thing to Z-order on. Maybe you chose like a string that never changes. We have statistics for it, but if you never use it, it's not great. Any new data that comes in needs to be Z-ordered, so it comes in how it comes in. Some of the different bits with, like, let's say you want to query by account ID. You have that good, nice Z-ordered old data. The new data comes in, you got to read all of that, so that's not great. you need to basically re-Z order that data, which ultimately leads to kind of rewriting a lot of data. So sometimes you have to make this trade-off. Do I have well-sorted data that makes these queries a little faster, a lot faster? Do I just have data and I don't pay for the maintenance operations? So there's some trade-offs to make because they can be kind of expensive. Oh, and then the other one, user error. So Z order columns aren't actually stored in the metadata. It's one of the few things that aren't stored in the metadata. So when you Z order a table, it'll go ahead and sort the data. And when you go ahead and you Z order it again, you actually have to specify the columns you want to Z order by. It doesn't pick that up from the metadata. So with Z order, you have to actually remember what you already have Z ordered by. Otherwise, you're going to have Z ordered data, but just with the wrong things to Z order on. All right, and we have a pop quiz. Oh. How are we doing questions?
By the way, folks that are standing, if you want to sit, that could also be good. Okay. This is the quiz that we wanted?
Oh.
No.
Let's ask it anyways.
Okay, sure, yeah. Okay, well this is just for fun. This is a guessing game. How many unneeded row rewrites do deletion vectors prevent per month? This is actually, I think this is actually just a guess the number. I don't think we actually covered. Why would we cover this? Yeah.
This is more of a fun fact.
It's a fun fact. That's a good one. Yeah. Not everything has a correct answer. This one actually.
This has a correct answer.
This actually does. Yeah. Okay, it's neck and neck between 10 trillion and 100 trillion. Oh, are people changing their votes? No, 10 trillion. Okay. Oh. Sunitha, what's the answer? You want to tell the audience?
100 trillion rows.
100 trillion. Oh my God.
Yeah.
Sunitha, how did you know that? Wow, are you an audience plant? Oh my goodness.
We'll talk more about deletion vectors and how they work in a little bit.
Yeah.
All right, good pop quiz. All right, so that's really like the core foundation of Delta. So all of those metadata things, the optimize, the Z order, the data skipping, partition pruning, schema evolution, those are all core capabilities. And if you look at Delta Lake, almost all of those capabilities are I would almost consider pretty basic. They've been around since like Delta Lake 1.0. But there's been a lot of innovation on top of Delta Lake. And it really stems from using those core features and that metadata to optimize it even further. So the first one that's really cool is going to be this new thing called liquid clustering. And if you follow Databricks or some of the louder people on LinkedIn, you've definitely seen us talk about liquid clustering. And the whole goal with liquid clustering is to remove what I like to call a foot gun. So a way that users can shoot themselves in the foot. So let's take a look at what the problem statement is here. So we have a table that has many customers and many dates. And we want to figure out how we should lay out this data so it's most optimal if I query by customer or if I query by date. And you'll notice with this data, some customers have a lot of data, some customers have a little data, some customers don't even have data for every day. And one of the things you'll notice is people will talk about over-partitioning, but under-partitioning is also a thing. And many times they actually manifest in the same table. So in this example, we have over-partitioning because these tiny customers don't have enough data to really have its own partition. And then the whale should actually be split up into more files because it has a lot more data. And this is what I get for using build slides. So the green squares basically just say what I just said. All right. All right, and then as we have new data come in, The more partitions you have, or the more columns you partition on, and the higher cardinality of those partition columns, the more files that get generated when you ingest the data. So there's this thing in Spark called Spark SQL Shuffle partitions. And when you write to a partition table, it actually writes one file per shuffle partition, which doesn't sound like a big deal. But let's take this example. You have a query that uses 1,000 SQL Shuffle partitions, and you're writing into 10 partitions, just 10 partitions. When you write that data, you're actually going to write 10,000 files, and immediately give yourself a small file problem. So as you add more partition columns, you're more likely to get into that type of situation. And here you can see, the more times you commit, the more number of small files you're going to have. So that's really the motivation for Liquid, is we want to prevent people from running into the small file issue. We want to prevent people from basically having to plan how their table is going to look for the rest of their life when they create that table. We want to simplify the user experience when working with Delta Lake tables. So when we're working with liquid clustering, it offers a bunch of cool features, but the first and most important, in my opinion, is it's super fast. So when you are writing to a liquid table, we do a little bit of eager clustering. So the first time you read it, the data is actually kind of clustered. It's self-tuning. So when you have different scenarios where users have more or less data, it'll avoid over and under partitioning, because Liquid is just a bunch of ranges. Liquid in itself is a flexible. That doesn't work. So Liquid's like water. It's, it takes the shape of its container. It's incremental. This is actually super, super interesting. When you work with Liquid and you do an optimize of a Liquid table, it's actually incredibly intelligent about only rewriting the minimal amount of files. So if you've run like an optimized Z order on a big table before, and you just added a tiny amount of data, and then your Z order rewrites like a terabyte of data, that feels really bad. Liquid clustering actually solves that. So because we have flexible ranges that we can go ahead and basically cluster this data around, it's resistant to skew. I've said flexible like 7 times, so it's definitely flexible. If you want to change the clustering columns, so with partitions, you say, hey, partition by date, and then we pull out one of the values from the file, and we store that in the directory. So if you ever want to change it, you need to go ahead and read the directory, generate that one value, put it back in the row, and then go ahead and rewrite the table as something else. With Liquid, you don't have that issue anymore. If you want to change how you store or lay out your data, you just change the clustering keys, and I'll show that. And it actually gets better concurrency. So with Delta, usually you kind of 1 or 2 writers at the same time, and you're very, very careful to make sure you didn't read anything someone else read when you do your updates and your merges. You don't have to think about that as much with Liquid anymore because it supports row-level concurrency. So that's a bunch of words, but what does it look like? So when we're working with a Liquid table, for now you do have to create a new table, but you're just going to do one thing different, maybe 2 things. So if you partition, you're going to get rid of the partition identifier in the DDL, and you're going to go ahead and add a cluster by. And you can cluster by none if you're not sure what you want to cluster by yet. Let's say you just want to create the table. Or if you're sure you know what you want to cluster by, you can go ahead and set it in the DDL. If you decide you want to change your mind later, they just do an alter table. When you go ahead and you optimize Liquid table, you no longer need to specify Z order or remember the keys, because the cluster ID is probably stored where? Transaction log. You don't need to worry about what are the optimal file sizes. Liquid's going to figure that out. You don't need to worry about whether a column can be used as a clustering key. And what that really means is that if you're used to partitioning, you would be pretty positive you're not going to cluster by timestamp, you cluster by date. With Liquid, just cluster by timestamp, doesn't matter. And then you don't have to worry about the order of keys. So if you've used Z-order before, you would notice that as you add the 3rd key or the 4th key, the file skipping gets worse on those keys. You don't have to worry about that with Liquid. So if we take a look at this in pictures, here's our existing scenario. With Liquid, we say there's no more rigid boundaries, so we can actually go ahead and merge files across those previously rigid boundaries. We don't have boundaries that are limited to one dimension. We can go ahead and switch dimensions in our clustering. We can cover multiple dimensions. There's no hard-coded value that you have to adhere to for your data. And if you have really heavy partitions or what would have been partitions, Liquid's smart enough to split those out. So you're not worrying about balancing file sizes. You're not worrying about balancing partition sizes. You're just not worrying about much. You're just picking your cluster ID or your clustering keys. And then for ingestion, so with ingestion, the clustering is stored in the transaction log, so we know when we write, eventually we're going to sort this data somewhat by these keys. So we're going to go ahead and write this data in, and we're going to pre-sort the data. So even if someone comes in and queries the latest bit of your data, it's going to be somewhat sorted, so their performance is actually going to still be pretty good. And then as we start to optimize, we start to split this into different sections, and we go ahead and we combine those, and we just kind of keep chugging along forward. All right. And one thing that's not mentioned is these blocks, as they're created, they can actually continue to merge into each other. So you see right here, we have these 3 blocks. Let's say the amount of data in those blocks started to change. Liquid would say, okay, I can merge these 2 together. So once they're written, they're not set in stone. And Liquid under the hood actually uses a better data skipping, or a better algorithm for organizing the data. So with Z-order, it uses a Z-sort. With Liquid, we actually use a Hilbert curve, which allows for better data skipping. It has better properties when you get to higher dimensions. Now, these Liquid clustering I mentioned creates an incremental experience when you optimize. So when you optimize a table, it basically assigns these files to what's called a Z-cube. So if you've already optimized some data, those files in the metadata get assigned a tag. The tag has a Z-cube ID. These files now belong to that Z-cube. And as new data comes in, we continually add that new data to that Z-cube. So at most, you're just going to rewrite part of this Z-cube. And when the Z-cube gets to a certain size, we just leave it alone. Once it gets to 150 gigabytes, we no longer need to touch that Z-cube. So instead of rewriting the entire data when you sort it, we just sort or rewrite things that don't belong to a Z-cube, and we find a Z-cube for them. As your tables grow, you can have many Z-cubes. So each Z-cube is 150 gigabytes. So when you optimize, at most, you're going to rewrite 150 gigabytes. When you remove data from the Z-cube, if you're doing like DML, deletes, or updates, the Z-cube will reach a threshold, and then it'll be eligible for more data to go into it. So these Z-cubes are somewhat flexible. And yeah, that's Liquid clustering. Super cool feature. You guys should definitely use it. That's one of our innovations. All right, so the next one, natural sort order. This is a super cool feature, and I feel like I say that every time I'm talking about another feature, but they're all really cool. This one is natural sort order. So one of the things that's really interesting is, or maybe not interesting, maybe obvious, is most people query data by timestamp, right? So data comes in, they want to look at like what's the last day, what's the last week, what's the last 2 weeks. So if you actually can, and then as data is ingested into a table, naturally it's data from today, data from yesterday. And then the next day it's data from tomorrow, data from today. So the data is already kind of naturally sorted by the time it comes in, or natural sort. And if we're able to maintain this clustering, when we're doing this, we actually have a well-clustered table, even if you didn't specify anything to Z-order by. What we do is, in the commit log, we store information about when the data came in, and if you just call optimize on a table, we actually keep it sorted by how it came in. So as we're interacting with this data, we don't try and blow it up. So what does that really mean? What is sort preservation? Basically, it's when you do any sort of DML command, you take in this base table, you do some updates, you do some changes. What you want to do is you make sure that the data kind of looks like it did when you started. So in this example, we have 3 files already in there, 1 duplicate. We go ahead and we merge in some new data, and the output is going to go ahead and look somewhat like it did on the input with the updated records. So it's really cool because Delta applies this whenever there's DML commands, and it does a really, really good job of keeping your data in a good shape. So when you're working with these Delta tables, you don't always have to keep running maintenance commands every time you do a DML update, because we do a really good job of keeping the data in the order that you already have it. All right. And we do that through being clever with our joins. So when we do a DML, so in this case, a merge, what we go ahead and do is we take the source and we take the target. We do an inner join to figure out what matches. We take all the files that have a matching row. We do a right outer join with the new data, and notice the right outer join is only shuffling the new data. We then go ahead and apply the changes, and then we write the data out. So because we read it in, we didn't shuffle it, we only shuffled new data, that existing sort still exists. The new data is then written out, and that new data is already clustered because it's the new data that all came in with each other. So we do a lot of things like this to basically make it so Delta, as you mutate it, still stays very performant. All right, deletion vectors, I think I gotta speed up a little bit. So deletion vectors, that's another innovation. A deletion vector is a way to prevent write amplification. Write amplification means when you have a record in a file and you update that file or that record, you would rewrite the entire file. So even though you changed one record, you'd have to rewrite the entire file, and that's write amplification. What deletion vectors allow you to do is they allow it to basically tombstone a row. So when you go ahead and you do a delete from a table, instead of rewriting the entire file, you can just write a deletion vector that marks a row for deleted. And then when a reader comes in, they can just read that data, or read the deletion vector, combine it with the file, and then show the user the data without that row. All right. The next cool feature is the change data feed. So I mentioned the change data feed earlier. The change data feed is a super powerful feature that I feel like is underutilized. So it provides a bin log, basically, of your changes. So as you do a merge or an update or a delete in a table, it's not always simple to just read the table, compare it to the previous version to get your inserts, updates, and deletes, and your changes. The change data feed just writes these as a separate record. So you don't even need to do that. So as you do this, it just automatically writes it out for you. Generated columns. So when you're working with a data set and you want to, you can't use liquid for whatever reason, so you need to generate a record or a value that has a higher or a lower cardinality from another value, so maybe cast a timestamp to a date. Well, you can do that with generated columns. So in this example, we're going to create a date, generated always as, casting the event time as date, and then we can partition by it. But what's super cool about this is instead of manually casting it in your code, where you cast, select timestamp as date, it does it automatically for you. So as you write to this Delta table, it automatically generates that record. So if someone else writes to the table and doesn't realize they need to generate that record, it does it automatically for them. But there's more. Because we know this is a generated column and we store it in the transaction log, we can use that information, and now we know timestamp and date in this example, they have some sort of correlation, so we can use this in data skipping or partition pruning. There is support for identity columns, so for the data warehousing folks, you do have the ability to let Delta automatically generate unique integer values. You can also do it yourself. And we'll just skip this. All right, semi-structured data. This is really fun to deal with until it's not. Semi-structured data usually is another name for JSON or XML. So let's take this example of a JSON record. When you're working with this, if you tried to make it about as generic and flexible as possible, you'd come up with this kind of struct type. You'd come up with a schema that's strings, integers, maps, and arrays. And this is actually pretty flexible. A lot of times you actually make it a lot more rigid, and it actually becomes really, really hard to evolve schema. So we're introducing a new type called the variant. The variant is basically going to make parsing and dealing with this JSON data very simple. It uses some tricks with binary encoding and storing metadata to make working with the variant super fast. And it also gives you kind of familiar ways to interact with it. So we'll get to that in a second. And it shows 4 to 20x improvement over working with JSON strings. So if you want to use it, you just create a variant type, and there'll be a lot more about this tomorrow. There's familiar ways to use it, so you can do a parse JSON command, you can use path navigation, you can flatten objects. And that pops to the pop quiz, and that's the densest part. That was dense. Well, it got a little lighter, but it gets better. Less dense.
It does. For folks who maybe need to take a picture of the QR code again, now let's see how much you captured from that. Okay, this is a fun one. This is another kind of a guessing game, I think, too. Since Liquid was previewed last year at Data and AI Summit, 30 exabytes have been read with Liquid. How many exabytes of data was skipped with liquid clustering? So a hint here is that this should be a bigger number than 30. And you can just write whatever you want here, hopefully just a number, because it appears to show up on the screen. Wow, people are actually pretty close. Okay, oh wow. Some people here are audience plants that got it. Yes, I see someone was testing. Oh my God. We got some people here who are just saying hi to their mom. Is she watching at home? One cat. Okay. Let's see. Okay, about tree fitting. Okay, thank you. Thank you all. This is what I get for putting a free-form response. There's another one upcoming, so we'll just have to make sure to skip some of those. The answer is actually 1,200 exabytes of data skipped with Liquid. So a pretty impressive number. Is there another? I think there's another pop quiz, I think here. Oh, no, there's not. There's not another pop quiz. It's later, and it's free form, so now I'm a little bit regretting that. Let's go back to presenting. Oh, it's me who's presenting. Okay, great. This is good. Okay, we're gonna switch gears. Okay, everyone, kind of like take yourselves out of. So now we got like really in the details, right? This is what you wanted. You wanted a deep dive into Delta Lake, and now we're gonna talk about Delta Lake with UniForm. Actually, okay, I didn't add a quiz for this, but who here has heard of UniForm? Okay, it's like half the room. Do you know what UniForm stands for? It's not Delta uniforms like Delta Airlines, by the way. Does anyone know? Universal format, yes. Wow, so smart, okay. This is good, it's a good name, it's a good name. Sari here is actually the one who came up with that name. So you can credit him if you think it's good or bad. Okay, so here's a little bit about the motivation behind UniForm, which is that so I'm a product manager, right, talking to a lot of customers, and something that we've heard a lot is that it's really difficult to know how to choose a data lake format. So customers feel like they have to choose. You have to choose Hoodie, maybe you have to choose Delta Lake, maybe you have to choose Iceberg. It's not clear necessarily like which of these is the best. Some of them are better for different use cases. They have different connector ecosystems. But as you can tell, they actually kind of look pretty similar. So you have Parquet files, and then you have some metadata that's on top of it. And so then we thought, what if you don't have to choose, and instead you can get the best of all worlds? So Delta Lake with UniForm says you have your underlying Parquet files, so you're not going to have to have multiple copies of data. You have one source of truth, the underlying data. But then what we can do is we can generate metadata for Delta Lake, for Hoodie, for Iceberg on top of that same Parquet files. And so what this enables you is then you're able to access all of these different connectors. So I think on the previous slide, right, there was all these different connector ecosystems that some of them are overlapping. some vendors, some engines lean more heavily or only support or provide better support maybe for one format or another. And then now we're saying, hey, you can access all of those. Wow, I see some people leaving during the UniForm section. Rate it 5 stars. Rate it 5 stars, y'all. All right, so here's how it works. I think I mentioned, so basically Delta Lake with UniForm, your data is stored in Delta and then can be read as if it were Iceberg or Hoodie. So metadata is automatically generated to make Delta accessible as Iceberg and Hoodie. Parquet files remain the same, and then the metadata is going to be co-located with the data. And so a little bit about how this works, or at least some of the motivation behind this, is that the key insight is that basically the metadata, there's differences, right? But it's actually kind of the same. So with Delta, I think we just talked about this, right? You have the Delta, like your source of truth requires you to read a bunch of Delta versions, like since the last checkpoint. With Iceberg, all of that is kind of self-contained into one manifest file. But some of the metadata and ultimately the stats and features that they provide can be kind of similar. And so then our key insight and observation is that it's very similar writes on both sides. So for example, a Delta writer, they write some commits. They'll notify the catalog of those commits, and then a reader is able to read from those metadata files. Iceberg writer, same-ish thing. You write data and metadata to the catalog, and your commits to the catalog as well. And so you can kind of see here, it's actually pretty similar. Basically, they both have this step of being able to notify the catalog of commits. And so UniForm concept actually unifies the write path. And so the idea here is that you can write once, and then you can read from both Delta readers and Iceberg readers with metadata, Iceberg metadata that's generated on a UniForm enabled table. So this is a table feature. You just enable it on the table, and then we'll start automatically generating Iceberg metadata to enable you to read from that same table from Delta readers or Iceberg readers. And so this is what it would look like on Databricks, for example. It's with using Unity Catalog. And then one thing that we'll be talking more about tomorrow as well, but one thing that is kind of cool is that Unity Catalog also implements the open standard for the Iceberg REST Catalog API, which means that any of those Iceberg clients, for example, say like Snowflake, for example, or Trino, would be able to talk to Unity Catalog as if it were just another Iceberg catalog and also be able to read from those same Delta tables that you had UniForm enabled on. And so just a little bit more about how this works. Basically, you remember like Delta Lake has those V0, V1, you have those versions, right? And that's your source of truth. What we do is then you have those versions coming in with Delta Lake, and then we'll actually go and generate, sort of in batches, the Iceberg metadata, version 1, version 2. That's kind of what this is showing. And then this turns out to be pretty nice because Delta Lake was designed with, commit, very fast. Iceberg is designed more around like slow moving data. Maybe, I wonder if that's where the name Iceberg kind of came from. Anyways, designed around slow moving data. And so this is actually kind of nice because you kind of get the best of both worlds. Okay, so I have another pop quiz. Let's see how much you got from what I said. I'm nervous about this because I'm nervous, you know why? Because this is another, I couldn't figure out how to do multiple select. So this is actually, it says A, B, C, D, but you can actually choose multiple of these. Let's try this out. I'm nervous about what I'm gonna see when I flip back to the other one. But basically, the question is, how can one read Delta UniForm tables? It can be multiple of the following. Read the table as Delta by accessing the storage location. Read the table as Delta by accessing the catalog. Read the table as Iceberg by accessing the metadata JSON path. Or D, read the table as Iceberg by accessing the Iceberg REST catalog. Okay, now I'm gonna switch to the other tab. Let's see what people wrote. Dogs and cats, oh no. 1,000 drop table users. Okay, well, some people got it. All of the above, thank you. All of them, UniForm rocks, thank you. I don't know who wrote that, but I really appreciate it. It's providing me a lot of moral support right here. So the correct answer is all of the above. Looks like most of you got it. Some of you decided to take this opportunity as your 5 seconds of fame. And I'm going to switch back now. We're definitely switching this for the next repeat session. This is a good learning. Okay, we're going to talk through a few use cases. So now, Joe and I just spent 70 minutes talking about how great we think Delta Lake is and what it enables, but let's actually maybe hear from some of our real world use cases and real world customers. Oh, wait, let me, is this presenting? Yeah, this is presenting. Oh, here, I'll do this. Great, okay. So here's one example, Columbia. The challenge here is that they have a lot of data in legacy systems, which could take weeks to ETL for analytics and reporting. And so as a result, unable to support a variety of use cases, right? And so with Databricks, they're able to build high-performance ETL pipelines. Those pipelines feed into Delta Lake, which then provides secure, performant, easy-to-use access to all that curated data in Delta Lake. And so they were able to simplify their data pipeline operations and then able to get efficient and performant access to the data, all with this open ETL pipelines to open file formats. And so the outcome here is there was a 70% reduction in ETL pipeline creation time and a 48x improvement. This is not a typo, 48x improvement in time to process ETL workloads, 4 hours to 5 minutes. Okay, here's another example, JB Hunt. They're in the manufacturing and logistics industry. They wanted to unlock the value of data that was stuck in legacy data warehouse systems. They had tons of data that basically their existing legacy systems struggled to scale. Their solution was to leverage Delta Lake as the open storage layer, which brought tons of efficiency and then portability. So that's that key aspect of having open storage formats that are all in that blob storage that you have like S3 or ADLS at terabyte scale. And so they were able to stream data real-time Delta Lake and then get high performance and reliability at any scale. Again, with a sort of single copy of data, and then they were able to build ML models atop this single source of truth. And so the outcome here is 99.8% faster freight recommendations and 2.7 million in IT infrastructure savings. And I'll actually talk maybe a little bit about what that looks like. Let's imagine you're JB Hunt and you're a data scientist there and you're trying to develop a ML model with Delta Lake. So this is an example of like a real use case, right? And so if everyone kind of knows that you've heard this, right? Good ML starts with high quality data, right? Garbage in, garbage out, gold in, maybe gold out. And model reproducibility starts with data reproducibility. And so we know that many factors will affect the outcome of the model, like adding new data sets, data distribution, sample changes, and all those things. And so Delta Lake actually makes model reproducibility really easy with features around data set versioning, change tracking, and full history and rollback. And so I think Joe mentioned earlier, for example, that when you're developing ML models, you'll frequently want to pin a specific version of the data set, and that's key for this use case, right? You want to be able to make sure that the model that, or the data set that you trained the model on, you're able to reproduce. For example, in this use case, say you had some initial model training, okay, ignore all this code or whatever, there's just some sample code. You're adding all this, you added all this new data. So first you had this initial model training, right? And you're using version 1 of the data set. You added all this new data, you retrained the model in version 2. You compare the model performance between version 1 and version 2, and model performance tanked. Wow, that's a bummer. This never happens to anyone, right? I don't know how many people here this has happened to. Oh, I see people taking pictures of the slides, that's good. Okay, so then what do you want to do? You want to roll back to version 1 of the data set, and you want to actually compare that between version 1 and version 2, so that way you're able to debug kind of what went wrong, and then see if, for example, if that sample change or if adding that new data set or something like that was what, for example, was causing your model performance to decrease. And so Delta Lake features such as rollback and history make it super easy to trace the lineage of all the changes to underlying data, which ensure that your model can be reproduced with exactly the same data that it was built on. Okay, and then I'll pass it over to Joe.
And one of my favorite use cases, almost every single customer at Databricks does this use case in some way, shape, or form. So they have some sort of application, and they want to replicate this data to their data lake. And they want to do it in a performant and efficient and cost-effective way. So the challenges are that it's really hard to basically version things as in large tables. So as changes are made and trying to understand what those changes were, you typically go ahead and compare all of the table, all of the data to the previous version. And when you're working with those and you're doing it in a batch format, it's really hard to give yourselves kind of near real-time type updates. So as you have users that are interacting with the data and they want to know what happened today. One of my previous companies, we didn't know what happened today until 9 a.m., hopefully, the next day. So having that ability is somewhat tough. And then having an audit trail of who's done what, how the records have come in, what's the process of what merges have been applied. And this is really how almost every customer at Databricks does this. They have some sort of external database. They have some tool to extract the data. So maybe you're using DMS or a sync sort or something. They land the raw CDC files in their raw layer. They go ahead and they use autoloader to ingest that data from raw into bronze, and maybe they put a very loose schema on it. They then go ahead and they have their fact table, their silver table, and they go ahead and take this raw data, they clean it up just a little bit, and they maybe merge or do an insert into their silver table. They then take those changes or those updates, and then they apply them to their gold tables. And the whole important part here is as we're doing it, we want to do it incremental. We never want to rewrite everything. We want to do things as efficiently as possible. So that's how you do it in pictures. But if we talk about the components that you actually use, this is a very typical pipeline. So you're going to start by using autoloader, and you use it in a read stream. So one of the interesting things with Spark is there's structured streaming. When you're working with autoloader and writing to Delta, everything's incremental. So if you start a stream and you stop the stream keeps track of what's been written, what's been read, and it knows when you start the stream back up, just go pick up with where I left off and process all of the new data. Now, autoloader is not the only source that supports that. You can actually read from a Delta table, and when you're moving from bronze to silver, you may apply some transformations, some data quality, some cleaning rules, and you want to go ahead and basically write that to a Delta table. And again, when you're using Delta as a source and Delta as a sink, you have that transactional, and it's all incremental. Finally, we've enabled the change data feed on our silver table. So we want to go ahead and just read the changes because we don't really care about rereading the entire table. We just want to know what's changed, what's been inserted, what's been updated, what's been deleted. So when we do a read stream, we just specify read the change data. Don't go ahead and reread all of the files, just tell me what's changed. And then they leverage merge, which merge is actually a super efficient operation if you use it right. Sometimes it's not so efficient, but it's pretty good. When you're using merge, it's really nice because when you do an update to a table, merge operates at the file level. Traditionally, you would basically update an entire partition, you do an alter table, add partition, and you would rewrite the entire partition. With merge, it actually operates at the file level, so we're only going to rewrite the minimal amount of data, and then if we're using deletion vectors, you have additional advantages on top of it. All right. Your turn.
Cool. All right. I'm going to talk a little bit more about the roadmap. Oh wait, is this me? Mm-hmm. Oh yeah. Actually, I'm gonna since we're running short on time, I'm actually going to go straight to the roadmap ahead. So there's three things that just generally that we focus on here at Delta Lake. We're always thinking about simplifying the user experience, so making it much easier to work with Delta Lake. The second thing is data integrity and reliability is paramount, and so there's some upcoming innovations there. And then finally, it's super important that we enable seamless interoperability with the broader ecosystem of tools that you may be using in your real world, like data ecosystem and architecture. And so in this first bit, we're really focused on simplified data management. And so something that we're working on is the ability to convert partition tables to liquid without rewrite. This enables an effortless transition to more efficient liquid clustering, which we have just talked up. for earlier in this session. And this is without needing to rewrite your partition tables. And so this is really exciting. You're able to upgrade your tables in place to liquid. Something else that we're working on is identity columns. So this allows you to easily generate a unique ID for each row, which is a super common use case for creating primary and foreign keys. And then third, type widening. So this, I think, has been long in the works. It's as data expands, it's very common to wish that you'd started with a larger data type. For example, you might have started with an int, but now you're running into integer overflow issues. And so with type widening, you can widen your types inline in your table seamlessly without data rewrites or workload interruption. And then finally, and then Joe just talked about this, variant data type. This enables a ton of flexibility for your semi-structured data, and we have more to come on this, and we're going to talk more about it tomorrow, Thursday, something like that. But yeah, variant is something that we're really excited about. Okay, second theme on our roadmap is data integrity and reliability. And so we really want to make sure to deliver high data consistency and availability across multiple environments. And so something else that we're working on, you can go see this being developed out in the open, is this concept of coordinated commits. And so all of these things that we just described around like those transactional guarantees, those rely on APIs or primitives at the file system level, not at the catalog level. Unlike, I just talked about Iceberg, they write to the catalog too. And so what we want to do is be able to have you specify commit owner for a table that's going to be responsible for coordinating those commits. So if you're writing from multiple different clusters, multiple different clouds, you can be able to go through this central coordinator, and that central coordinator is responsible for maintaining the transactional guarantees and making sure that, if you shouldn't be able to commit or there's a conflict, something like that coming up, that the right thing fails and you're able to have the freshest metadata. And so what this can enable is like cross-region disaster recovery. So once you have this idea of like, okay, now I have this commit owner that's responsible for knowing all of the freshest like metadata and the freshest version. What's the correct version? So basically it becomes your source of truth for your Delta table. What this enables you to do is accurately replicate this metadata across regions, which helps with disaster recovery. And so this is something that is very important to our customers, and so this also helps to unlock that. And then something else that we're working on is collations, which is custom sorting comparison rules. So collations allow you to set these rules for strings based on the appropriate language or cultural content. This is often crucial for applications that handle international data. And then finally, Spark Connect support. So as you may have heard elsewhere, Spark Connect is a disruptive new architecture for Spark. And this changes Spark to a client-server architecture, which will improve debuggability, upgradability, and reliability for your Spark applications. And then Delta 4.0 will have full support for Spark Connect right out of the box. Cool. And then something else, and then I'll have to plug another lightning talk on this by a colleague later. Something that this enables, the coordinated commits that I mentioned earlier. Something else that this enables is this idea of multi-statement and multi-table transactions. So once you have this centralized coordinator, all your commits from all these different writers that you have across clouds or clusters, they're going through this centralized coordinator. That coordinator can also help you coordinate these multi-statement and multi-table transactions. So for example, you have like multiple different tables. It'll know, okay, if a write to this table failed, then I should know I need to roll back the whole transaction. And so this will enable us to have greater atomic transactions. And this is something that I know people have long awaited and are very excited about. And then finally, we're focused on seamless interoperability. So this, the reason you should care about Delta kernel, I guess I should say, is basically Delta kernel. It's a library for Delta connectors that abstracts the Delta protocol in this like easy set of like core library APIs. So basically it makes it really easy for connectors that have integrated with Delta kernel to be able to get the latest features. So all these innovations that we just talked about, deletion vectors, for example, being one, where say you have like one version of a Delta writer, which is like writing with deletion vectors, but then you have another Delta reader elsewhere, which maybe doesn't support being able to read tables with deletion vectors. That might be something that you might encounter in the wild. This helps with that. So Delta kernel makes it super easy for clients that integrate Delta kernel to be able to just get those latest innovations. So being able to read tables with deletion vectors, for example, by simply just version bumping your Delta kernel. And then, so as part of that, we're constantly working on expanding the connector ecosystem. And so we're going to be collaborating with the community and partners to build connectors with kernel. We're going to be announcing some exciting upcoming one. I do have to plug one that's my favorite. So I'm gonna harken back to the beginning of the talk with the puppies. There's one partner that we're working with. They're called Puppy Graph. They're a graph query engine. But anyways, they have a great name, and we're also working with them on a connector with Delta kernel. And then finally, Delta UniForm. So I talked about this, but basically one of the things that we really want to make sure we're enabling for customers is that we want to improve interoperability with the latest Delta capabilities like deletion vectors with Delta UniForm. And so there's an analogous feature in Iceberg, for example, which is like position deletes to deletion vectors. And so what we want to do is enable an interoperability between those features across the formats as well. And so you're able to get all of that awesome stuff with this incredible interoperable connector ecosystem. And so with that, I think we've pretty much wrapped it up. And so thank you so much for spending 87 minutes with me and Joe.
It's a big commit.
It is, oh my God. How long have you been sitting on that joke?
Like 5 minutes.
It was a big commit. It was a big commit. We'll write a checkpoint file after this. So learn more at the summit. So first of all, you should, by the way, everyone, me and Joe, we have a bet going with some of our teammates on the ratings for our talk. And so it's very important that we win this bet, all right? And so please rate our session very highly. And then there's a lot of other things you can do next here. And then also, here's the QR code for the Databricks events app. And then I'll also plug some of our upcoming sessions. There's a breakout session on Delta kernel, if you're interested in that. A lightning talk on going towards multi-statement and multi-table transactions, which talks more about that coordinated commits feature that I mentioned. And then if you're interested more in like this interoperability between clients, and if you're interested more in learning about Unity catalog interoperability, I'm doing a couple sessions right after the keynote on Thursday around enabling open data lakehouses. And so make sure to check those out. Oh, and then I'll plug another talk too on managed tables and how we're making them easy, powerful, and interoperable. There's a repeat session of that also on Thursday, I believe. Yeah, all right, did I get everything, Joe?
I think so.
Okay, okay. All right, thank you all.
Thank you, everyone.